and innovation. So my background is in risk and science and technology studies, and therefore John Downer is somebody I've known for many years. I've known his work, followed it for many years. He's a senior lecturer in risk and resilience in the School of Sociology, Politics and International Studies at the University of Bristol, and he's involved in their TAS node here, and he's going to talk to us about that. But I'm also hoping that we can utilize our common roots in science and technology studies, and in particular John's background, because he's been working in the nexus between science, risk, and governance, and issues in relation to the nature of expert authority. And people may know his paper "When the Chick Hits the Fan," which also is one of the classic papers in the sociology of testing, which show why tests may not always behave in ways that we expect them to, and the results of tests may not mirror accurately the performance of real-world settings. So I think we look forward to hearing about the work of Bristol, and in particular, we look forward to having a discussion towards the end. I know you're involved in the regulation work package on the Bristol TAS node, and we think that we have a lot of things to discuss with you there. So if you give us your presentation now, then maybe we've got an hour, but it'd be good to leave good time at the end for a discussion of our common interests, and people are likely to intervene with questions if you're happy to have that, or they'll post questions, but some of them you can take at the time, and others you may want to take later. I should flag to colleagues that we're recording this session, but we won't be attributing individuals, and if people want to pose questions anonymously, they can put them into chat, and I will read out their questions anonymously if they're worried about being so identified. John, it's great to have you here. Over to you.
Great, thanks, Robin. Very nice to see you. Let me see if I can share presentation here. Okay, yeah, hi. Yeah, thanks for that generous introduction. Yeah, as Robin said, I'm a senior lecturer in Bristol. Yeah, I was when this talk came along, I sort of framed it as a kind of introduction to the node, and yeah, they sort of, I volunteered to do it because you guys are the government and governance and regulation node, and I'm the regulation guy on our functionality node. So yeah, that's kind of what I got. So I'll go through a sort of brief overview of our node. Yeah, sorry about the slightly funky formatting throughout this. Bristol, I've been dealing with IT things all morning. Bristol revoked my editing privileges on PowerPoint for some reason. So I thought I'd start with a brief overview of the functionality node, its aims, its teams, and its structure, and then give you a sort of quick sort of survey of the kind of landscape of its work packages, and then drill in a bit more detail in the sort of regulation and governance work package, which is my stuff. Yeah, okay, so this is the group. Shane Windsor in the top left there is the PI of our team. We're all based in Bristol, which I've discovered is actually quite unusual for most of the nodes, but there's a sort of logic to it, which I'll explain. Professor Kirsten Eder in computer science, Jonathan Ives in ethics, med school, I think. Sabine in robotics, Jonathan Roster in robotics, and then me in space, as it's known, sociology, politics, international studies. Yeah, half of us are called John, which gets very confusing. Yeah, project partners. I'm going to try and move through these fairly quickly so we can get to discussion. So yeah, the pitch for the node was that we were interested in evolving functionality, right? This idea that the functionality of autonomous systems changes over time, right? Via generations of systems and so on, right? whether it be through, there are now, autonomous systems are sort of learning and adapting, and we're interested in exploring how this facet of autonomous systems, the implications of it for things like specification, design, verification, validation, so on. Regulation would be my part. So these are sort of objectives. Investigate how evolving functionality influences the way systems need to be specified, designed, validated, curated, regulated, and then design for trustworthiness for evolving systems, and then use techniques to develop sort of trustworthy autonomous systems, right? So there's a slightly more specific ones there I won't read out. So we've got this sort of interesting structure, right, where at the heart of it are these three work packages run by engineers who ultimately just sort of want to build robots, right? And around them we have these other sort of work packages that are sort of interacting with them and looking, using these various endeavors to build robots as sort of case studies through which to explore the more sort of social sciencey or more, the things like specification, regulation, so on, right? So normally, at least, we're all based at the Bristol Robotics Laboratory, or at least the node is, right? The kind of really interesting space full of people just building robots of all sorts of different kinds. It's University of Bristol shares it with University of West England. It's a sort of slightly independent, sort of co-owned hub, and certainly the idea when we planned the node was everyone would be building their robots there, and the RAs would be hanging out doing sort of ethnographies or epistemographies, as Peter Day likes to call them. Of course, COVID happened, so we've been sort of trying to adapt. This is the plan going forward, at least. Certainly, the semester's just kicking off with people starting to move into the lab, and we're hoping that this is how it's going to be going forward, right? But hasn't quite been how it's worked out so far. Okay, so someone made a flow diagram of everything that I just said, basically. There really ought to be a sort of sociology of flow diagrams and their relationship to organizational practice. But I won't dwell too much on that. All right, so the work packages. Let me go through these in a bit more detail. So start with the three robot, people building things. Sabine with her RA, James there in the corner, they're building swarm robots, right? I think what they're specifically interested in is kind of warehouse robots designed for adaptiveness more than efficiencies, right? So warehouse robots that you can use in sort of pop-up distribution centers and things that aren't very, very structured environments where you can really sort of optimize for efficiency. And swarms have all these interesting properties that I'll sort of come to in a bit. Jonathan Roster with Anthony and Alex there are interested in soft robotics, which I didn't even know was a thing until I joined this project. But are really interesting, right? They have all sorts of applications. I mean, soft robotics, as what it says on the packet, basically, it's floppy robots with all sorts of applications, ranging from sort of medical, designing tiny things that can potentially go into bodies, to gripping, to locomotion, sort of suits that will help with mobility and so on and so forth. And again, I'll sort of circle back to this and what makes it sort of interesting in a sec. And then Shane with Sergio there, his lab is interested in UAVs. Two specific projects I think that he's got going on. The one looking at biomimicry and morphing flight surfaces for flight, and another one for having UAVs navigate complex sort of urban environments. yeah, he's using a lot of sort of machine learning and deep learning to make these things happen. Unlike the others, I think Sabine's not using that, surprisingly. Yeah, I think she's creating decision trees with her swarms. Okay, so these three kind of work packages make for really sort of interesting case studies. Well, certainly we contend because they represent very different sort of functionalities, right? With all sorts of kind of fascinating implications, right? So soft robotics. Well, soft robots have a huge number of degrees of freedom, right? It's very difficult to say exactly where your robot's going to go or where it is at any particular moment, right? So, yeah, so that's a sort of interesting dimension of that, right? Plus the incredibly varied use cases, right? From yeah, medical to we had a discussion with someone that was using soft robots to dig holes for cables and so on. The swarm robots have these sort of interesting properties, right? They have kind of emergent and unplanned behaviors, right? You don't specify exactly how your swarm is going to achieve what you want it to achieve, and so you don't know exactly in advance. So that has all sorts of interesting sort of regulatory dimensions. Of course, the swarm is more than the sum of its parts, right? So if one bit goes out, you can potentially the rest of the swarm can adapt to it. And again, this is a kind of new, regulation doesn't normally think along these terms, right? We tend to think of validating specific elements of a system and sort of working up that way. Whereas, so swarm robotics have these interesting qualities, and then UAVs, certainly Shane's have these dynamic airframe structures, which someone that's written quite a lot about aviation, kind of interesting to me. He's got the deep learning going on and these very complex environments that he's interested in, and certainly UAVs. The environments that he wants to fly them in are interesting because UAVs are traditionally sort of flown in extremely open and forgiving environments, right? The sky's really big, it's very difficult to crash into stuff, right? But flying them in much more complex and populated environments again raises a whole bunch of sort of issues. And these properties and constraints, these properties create different constraints and pressures, right? The costs of failure is different in a very, if you're talking about medical or construction or so on. Environmental uncertainty and stuff like that. And so I'll sort of come around to this. Right, and so then the other work packages around these three kind of engineering packages. We have one on specification. Interested in this is again Shane's running this with Daminda. The approaching sort of, and a lot of these work packages, these sort of circumferential work packages, do cover sort of similar territory, albeit in very different ways, right? So, they're interested in what it says, right there. How do we specify the requirements for autonomous systems, with these complex and varying functionalities, right? But they're coming at it very much from a sort of engineering perspective, right? That tends to likes again flow diagrams and it's very mathematical and tends to think of these as ultimately sort of solvable problems on some level as sort of engineering problems. Kirsten sort of approaches verification same way. With RA Greg there, very interested in once you've got requirements, how do you meet them, right? How do you prove that your autonomous system is going to do what you require it to do, right? Irrespective of what it is exactly that you require. Again, approaches it very much from a sort of engineering perspective. Kirsten's in the computer science department. I think she's into sort of formal verification methods and very well known for it, I think. And then the ethics package, again, now we're moving into sort of the social sciences. Jonathan Ives and me are the two sort of social scientists. Jonathan Ives and Ariana and Helen is RAs. John's an empirical ethicist, right? He's medical ethicist by training, which kind of works because, well, partly because some of these robots, these autonomous systems have medical applications, but also because medicine is where sort of ethics really, the rubber really hits the road, right? They really have to, they thought very hard about ethical issues and ethical issues in real world circumstances, right? So John's an empirical ethicist. He's interested in working from not sort of idealistic ideas of how the world should be, but working from a place of, how the world is and what people actually think about things, and then sort of, working towards building a sort of ethics on that, or certainly in relation to that, right? He doesn't want ethics to be a sort of abstract thing. I think the plan is to explore how people's feelings about systems evolve as their sort of functionality evolves. And okay, so yeah, that brings me to regulation, which is my part with Pete Winter, who I think is here on the call. Hi, Pete. Thanks for joining. Well, we have a fairly narrow remit, right? I've been trying to, with a regulation work package of the functionality hub of the Trustworthy Autonomous Systems project, right? So we've been trying to thread that needle, right? So we've been trying to explore how regulatory considerations might shape engineering decision-making and expectations, and to outline a sort of conceptual framework for understanding and anticipating the regulatory implications of evolving functionality, and explore how considerations arising from engineering and verification ethics can be reconciled with sort of broader concerns that make up sort of regulations, the legal dimensions, and then the sort of pragmatic dimensions and kind of bureaucratic concerns and constraints of real world sort of regulatory oversight, right? So we've got these packages that are looking at sort of ethics and verification and specification and so on. But as this moves into sort of practical regulation, you encounter sort of organizational sociology and limit and things like this. So we're touching on a lot of the stuff that all the others are we're drawing on, so verification and ethics and specification, but also sort of building it out in a slightly, what I would argue is a slightly more rounded way. Bringing in these sort of wider concerns and looking at how will we make rules to govern these things, and what will we have to think about. And so the way we've sort of thought about kind of moving ahead with this is to think of functionality as essentially having two kind of core dimensions, right? Certainly in its common language sort of usage, right? Your functionality tends to, we invoke it in different ways to mean slightly different things, right? On one level, we invoke it to mean the purpose that a system serves, like what it does, right, what its function is. But we also invoke it to mean the manner of a system's functioning, right, how it does what it does, right, which it's designed, right. It occurs to us as systems evolve in these dimensions, you get these kind of interesting sort of regulatory issues that sort of arise, right. So if you think of functionality as the role that a robot plays or an autonomous system plays, then as that changes, then you get these changes in regulatory issues, right? So the UAVs that operate in the sky or outer space in a very extreme case, of course, have very different implications than UAVs that operate in crowded, dense areas, right? Or robots that operate in space versus robot homes, right? An identical robotic arm that stacks boxes, of course, is going to have very different sort of regulatory requirements than one that performs, heart surgery, right? So you can keep the technology stable, change its use, and then of course the regulation sort of changes around it, of course, right? And then the often in quite radical ways, which I'll sort of circle back to in a minute. Reliability is kind of something I'm interested in, so I pull that out. And then if you think about functionality in the other way as the manner in which a system performs a function, right? You can imagine a system performing the same function, but its design changing. Again, that has different sort of regulatory ramifications, right? So a traditional sort of mechanical arm as opposed to a soft robotic arm can have very different regulatory requirements, right? You can't specify a soft robot in the same way that you can a sort of mechanical one. As say cars have, as cruise control has gone from full self-driving on Teslas, right? It's a very different type of system. You've got deep learning involved, right? And you can't sort of formally verify your software anymore. You kind of approach it in different kinds of ways. So yeah, one of the things we've been thinking about with the software robots, for instance, is this tension maybe between degrees of freedom that a robot has and its controllability, right? So certainly John Roster argues that the more degrees of freedom that you give a soft robot, the more it can potentially do, right? The higher its functionality, it can do all sorts of complicated things. But the less well you can know it, right? So what they're playing with is limiting the degrees of freedom of software robots in order to make them more knowable, regulatable, verifiable, and so on. So some tension there. And then, what we're trying to look for is, Pete and I guess, the kind of guiding principle, we're looking for sort of critical differences. We're looking to identify sort of points in the evolving sort of functionality of a system where differences of degree become sort of differences in kind, right? You say, well, look, I think if we can kind of pull those out, we could say something really interesting about the relationship between functionality and regulation, right? So to give you a couple of examples, I already gave you the example of, deep learn, machine learned algorithms needing to be validated in ways that are different from sort of hard-coded behaviors or hard-coded software, right? That you can kind of formally verify hard-coded software, and it gets a bit complicated there, but it isn't a black box in the same way as sort of something like Tesla's autopilot is. More interesting to me, I think, certainly more relevant to work that I've done before, that I'm sort of interested in points where when the reliability you expect of a system changes, you can get very profound differences in sort of regulatory requirements, right? So it's not simple. It's, moving from a sort of box stacking robot to a surgical robot isn't just a simple case of, it needs a bit more of the same, right? At the levels of reliability that you want for sort of surgical robots, you can't measure or validate that reliability in the same way, right? Partly because you can never test anything to that level. You'd have to run it for billions of years in order to sort of empirically sort of verify that it was as reliable as you wanted it to be. But also because what very often happens is, as almost inevitably happens, is as reliability requirements rise, so too does the need for that reliability to be known prior to that system being used, right? Because if it wasn't that important that it be known prior to the system being used, then the reliability probably didn't need to be that high. And that, of course, raises all sorts of issues, right? You can't just, you could prove out a box stacking robot by letting it stack loads of boxes and counting how many it dropped. You couldn't do that with a heart surgery robot for very obvious reasons, right? You couldn't just count the mortality and say, well, we're getting there. So these kind of differences where changing various dimensions of the functionality become sort of require sort of kind of restructuring of regulators. So you get interesting sort of something I meant to say on an earlier slide. Let me just skip back very, very briefly. So as I think you get this kind of interesting effect as the sort of design of a system changes, where the regulator and all the rules you have in place for overseeing that system suddenly isn't, fit for purpose anymore, right? The regulators that oversee cars and automobiles, they don't have a ton of expertise in deep learning and so on, and organizations are very sort of slow to change, right? And of course you get the opposite as you have the same system move to different sort of functions, then suddenly they find themselves in completely different regulatory regimes, and of course that's kind of very jarring from a kind of engineering point of view, right? You've built something for a regulatory regime for box stacking, and suddenly you're subject to sort of medical requirements again. Yeah, so you can have the same system moving between regulators, or you can have one regulator sort of suddenly having to deal with very different systems and having to sort of, organizations aren't that nimble in my experience. And so that kind of brings me to the end. So one of these sort of crucial sort of points, so Pete and I have been trying to work through, and that I thought would be really interesting to sort of maybe discuss with the you guys, was this problem of when do we say a system is autonomous, right? Because once you've sort of declared a system to be autonomous, then of course you probably want to bring different regulations into play, or if you're going to regulate autonomy at all, you're going to have some sort of boundary where you say, okay, these things are autonomous and those things aren't, right? But it's not that simple, because when you look at it closely, I mean, everything, every machine replaces human labor to some degree, right? And we don't call them autonomous, right? The ballistic missiles don't have pilots, but we don't really think of them as autonomous systems. And then even the most autonomous systems, as with most humans, require some level of human oversight, right? Nothing is completely autonomous, right? So where automation ends and autonomy begins, I think is a really important distinction that we kind of have to work through or feel out if we're going to sort of say anything meaningful about, certainly about regulation. And I'd be really interested to know anyone's thoughts on that. So I'm going to end there and say thanks. I'm going to stop sharing if I can. I don't know how. Stop presenting here at the bottom. Okay.
Thanks, John. That's a question has been posed, which I think follows on to your last point, from Rama Murphy, who leads our node here. He says, you're describing a range in terms of nearness to deployment. For example, there are surgical robots today which are really teleoperated machines, and these are bringing up immediate regulatory issues that we have to think about. But adaptive soft swarm robots are quite far into the future in terms of being productizable. How does this play into your thinking about regulatory requirements and what needs to be assured? The difference between, things still being developed and those now in use.
Okay, sorry, I'm just navigating Teams a little bit. There are surgical robots. Well, the kind of surgical robots that we have today tend to be these tele-remote things, and again that gets us back into this sort of question of, what is that, an autonomous system? Or the same's true of a lot of sort of predator drones and stuff like that. We conventionally we tend to sort of refer to them as autonomous systems, but they're not really. Right? Maybe.
Could I maybe clarify the question a little bit? So the thing I'm thinking about is really that, I mean, implementing AI systems is hard, and we know that, and as an AI person, I know that. But there are some kinds of AI systems in which the regulatory approach need not be that different. Meaning that the existing way in which a regulator says you may do this, you may not do this, you should prove this and not, might still apply, in the sense that the way in which we arrived at, let's say, a controller required a different way of training it, but ultimately it's a controller and it's a fixed object. And in that sense, it's not different from a piece of code that is also equally inscrutable to a non-programmer. On the other hand, the things you're referring to, the idea that a system can change its functionality as it goes, it can choose for itself. These things are exciting, but I don't know of many products that have them quite yet. In fact, I don't know of any product that is truly kind of evolving in that sense. So I'm trying to understand sort of what is the pathway for regulation. So from what is today and we need to do to, one day when these things happen. What's your thinking on that?
Sure. Yeah. Certainly, we're looking forward to anticipating problems that might. I think that's where it gets really interesting. I might push back on a few things. Right, that it's not immediately clear to me that if you replace a human with something, you can necessarily sort of validate that out the same way, or just because code is inscrutable to the average layperson that it's inscrutable to regulators or in the same.
No, I didn't mean inscrutability. I think what I mean is there's an existing procedure for dealing with large code bases in the regulatory process. So for instance, aviation sector routinely does that kind of thing. And some of that regulatory process transfers over in the same way, and it doesn't matter so much for that regulatory process that some bits of it involve, let's say, a learning algorithm instead of, I don't know, some other optimization algorithm. It doesn't fundamentally challenge the procedures. Whereas you go a little bit further, and if you had something like what we would call continuous deployment in internet technologies, then it does challenge the procedure, because at no point can you pin it down and say, this is what the algorithm is, because the algorithm at 3:25 p.m. might be different from at 9 p.m. So I'm trying to understand sort of what is the pathway from things that work, like in aviation, like in medical devices, to what would be the intermediate step before we start looking way out into the future of things that don't yet exist.
Yeah. A couple of things, I guess. In terms of things that I don't think I would contest that this was way out in the future. I think the Tesla's autopilot is a good example, right? A deep learned system that is on the roads right now, driving. I'm not sure what the laws are here, but certainly driving Americans around to some extent, right? And very much sort of based on a very inscrutable algorithm. And as to whether that really changes I have complicated feelings about this, because I think even sort of hard-coded enormous algorithms, you can't sort of formally verify them in quite the way that. But certainly this is the language in which we talk about them, right? Certainly the language in which regulators talk about them, and if you can't get all the way to the many degrees of reliability that you need, right? The sort of 9 nines, you can get a long way with formal verification, certainly nothing, right? When you've got these sort of things like Tesla's autopilot, which are totally, they're really inscrutable, right? You can't even pretend to go through the motions of regulating it by scrutinizing the code half to death. I mean, how then do regulators approach that question, right? I think these are meaningful issues and more immediate issues than perhaps and then medical, you've got sort of medical diagnostic stuff using deep learning and so forth. I mean, I don't think these are they're not science fiction, and I think they are things that we do need to sort of think about on some level.
Daria, you have a question. Do you want to put your camera on, Mike?
Yes. If it works. Does everyone see me and hear me?
We can hear you, but not see you.
Okay. So there is a problem with my camera. All right. Okay, the camera doesn't work. Anyway, so yes, you mentioned a very interesting point that there is a trade-off, such as the degree of freedom and controllability. And and I personally, I also look at the regulatory frameworks and specifically about systems in the medical sphere. And whilst swarm robots are completely different than teleoperated surgical robots, there are some similarities in the sense that there's also a trade-off, I think. in terms of transparency and accuracy. So if it's not transparent enough, then there's a degree that errors might occur. And my impression is that regulatory frameworks such as verification do not take account of this kind of inherent risks and trade-off of any kind of system. And we need more attention to that. What are the inherent values we're trading when we employ such a system in a specific context? So far, it's just about outlining and making sure to give an assurance that the system is safe and secure with a specific function. But we don't really consider that dynamic balance that is always at risk with any kind of system, whether it is in the near future or not yet on the market. So.
Sure. I mean, I think I agree with that. You're saying that as systems become less transparent, they become more risky, which I think it seems intuitive to me.
Stuart, you have an interesting question. Do you want to come in next, and after you, Shannon?
Okay. So people have lots of individual vehicle accidents. Yeah, each person probably has a few at most. I mean, some of us maybe have more than others, and then they're involved.
I've lost audio, I'm afraid.
Now you've muted yourself, Stuart.
You're correct. I have. Yeah, that was me hitting a button accidentally. Okay, so people have lots of individual vehicle accidents, each person having a few at most. Yeah, and their involvement's treated on a case-by-case basis. But it seems that with autonomous driving software, all operating instances are identified as a single entity. So it's like you have one person driving a million cars. So do you think this is a supportable position? And is it an appropriate starting point for regulation?
Yeah, great question. Yeah, this is something else we've been thinking through a little bit. I mean, how safe do autonomous systems need to be, right? Well, what I think we're seeing right now are the sort of these two sort of logics confronting each other, right? This traditional sort of machine risk regulation philosophy that wants everything to be safe to one in every billion operations in some cases, confronting this sort of logic of, well, these systems are replacing humans, and humans aren't that reliable, right? So when a Tesla crashes, you see this play out in real time. They say, well, look, this has killed X number of people. And then Tesla comes along and says, well, people die all day. It's killing fewer people than, than if it wasn't there, right? And I think we're going to have to sort of work through that as a society. I think one of the difficulties in that is very, very difficult to make these kinds of statistical claims, right? So when Tesla says something like, our autopilot is safer than the average driver, well, is it that? I mean, the autopilot cuts off if it gets into a really tricky position, right? So, is it just safer than the average driver on the kind of bit of motorway that autopilot's happy operating on, or the control for all sorts of variables? Is it safe as the motorway driver? So on. I think you understand.
Yeah, but I also think there's another side to this, because if you look at most of these systems, they do need to be localized in the sense that, things like Tesla, they operate with very highly detailed maps of the local vicinity. And it's quite possible that they might be learning things about the local vicinity. And so actually those instances, I mean, once upon a time, if you look at let's say a primary shutdown system for a nuclear power plant, then that would be the same for every copy of the power plant. But here we're not talking about that anyway. We're talking about things that actually have substantial localization potential and may also have learning built into them, and may also include quite substantial configurable elements that are configured by the driver. So there's a sense in which, under what criterion is it justifiable to identify these things? because your version of your Tesla might actually be quite different from my version, even although they're driving around on the same bit of road.
I don't know enough about the internals of how that works to know how different cars are between each other, but it is just this question of how safe there are. I think in regulating autonomous systems in general, we're going to have to work through a whole bunch of sort of asymmetries, right? One of which being simply that accidents prevented aren't visible in the same way as accidents caused, right? So every time a Tesla saves the life of someone that might otherwise have swerved into traffic, right, that doesn't register as a data point anywhere, right? That it's very hard to pull that out.
But I think from okay, I'm going to shut up in a minute. But I think from a kind of legal and regulation point of view, I mean, I think the big thing that people like, I don't know, Waymo and so on are worrying about is class actions. Yeah, and the issue here is to what extent is that a supportable? Having a class action, is that a supportable position? Because it certainly would be eroded relative to, if you like, a standard. When you have something like the sorts of things that people are thinking about for autonomous vehicles, sure, then the notion of being able easily to identify these things gets more tricky.
Yeah, no, I do think they raise a bunch of kind of interesting liability issues. This is another thing that we've been talking to sort of lawyers about. If a autonomous system of any kind, so stick with cars, right? If autonomous driving could make cars 10 times safer than they are today, but made the car manufacturer liable for every single accident, then there's all sorts of perverse incentives in that, and it wouldn't be in Waymo's or Tesla's interest necessarily to push out a system that would be safer for everyone if they then had to sort of pay for every accident personally, right? So these are issues I think that we're going to have to work through.
Yeah, I should get out your way and let Shannon in. Yeah, sorry.
The question. Shannon, do you want to come in? Shannon Valor.
Hi.
You're muted, Shannon.
I know.
You've muted again. Oh. Speak. I think we can hear you now.
Hi, I'm sorry. I'm having computer problems. It's not responding to my mouse is not responding. So sorry about that. It wasn't really a question, just so much as an observation that I put in the chat, which is that with something like Tesla, we're currently reliant on other parties to tell us when Teslas are hitting police cars and fire trucks, and we have no idea how often they nearly hit police cars or fire trucks, but are diverted by an attentive driver. So the point being that without these former methods of verification and safety assessment, regulators have no idea what is a reasonable prior expectation of failure rates, and are relying on the companies or third parties who may have perverse incentives to underreport these problems. This is all fairly obvious. I just wanted to point out that with opaque or otherwise difficult to verify and validate systems, we're really facing a far bigger regulatory gap and incentive problem than in other kinds of technology.
Yeah, no, two things I'd say to that. The first, I think you're absolutely right. I think where you've got these sort of black box, deep learned sort of algorithms like autopilot, the only way that you can kind of prove them out for regulators is from service data. But then, of course, if people are taking over and avoiding accidents, that's not getting registered, and that's incredibly difficult to capture that data, right? That's it's an enormous problem that I think needs thinking through from a governance perspective. But on a slightly broader, I think this idea of being dependent on manufacturers for regulators of high technologies being dependent on manufacturers for their data, with potentially manufacturers with perverse incentives, I think is actually incredibly common. Certainly civil aviation and civil nuclear is exactly the same, right? They're heavily dependent on the manufacturers to do 90% of the, or more than 90% of, in civil aviation, the manufacturer airframers write the rules to some extent, right? Right, and they oversee their implementation. Actually, I've literally just finished a book about this. I think what makes civil aviation so safe on some level is the fact that it's really not in airframers' interest for planes to crash, like at all. If your plane gets a reputation for unreliability, it can just kill a airframer dead. It killed McDonnell Douglas, and you're pretty close to killing Boeing almost. And because we build planes in such large numbers, that you could expect unreliability to sort of manifest fairly quickly. Whereas I don't think that's true of most, and I think that might be true of sort of automotive as well, right? With millions of cars on the road, if your system isn't as good as it needs to be, then you're going to get blown. But that's going to become evident fairly quickly, right? I don't think that's true necessarily of nuclear plants, for instance. I mean, we build.
John, the Dreamliner case shows that it's in the perceived interest of the private manufacturers to achieve that domination over their regulators, even though in this case, two very high-profile accidents, one after the other, pushed that close relationship into careful scrutiny. But they were very happy to exercise that control right up until the safety case for their Dreamliner collapsed in the rubble in smoking rubble on the runway. So there's an interesting question about the political economy of regulation in that.
Well, can I just jump in and say, but I do think there's a salient difference, and the Boeing case is a great one, because in the case of the 737 MAX, at the very least, the regulator was able to look at the proposed design and see that the new mounting of the engines was going to pose a risk and was going to require some mitigations. Now, because of the regulatory capture, the mitigations were not the ones that were adequate. But that's still a case where a regulator can look at the design and say, okay, when we look at this, we can see that this design is going to pose an unacceptable level of risk. And that's just harder to do when you have these models where the types of failures that we might see are just not as predictable. So that was the comparison that I wanted to draw.
Yeah, I mean, there could be something definitely to that. Although I think regulatory capture is maybe the wrong lens to think about. I mean, high technology regulators are just captured. They are, because they just don't have the technical intimacy to make the kinds of judgments that they need to make, right? So, this idea that the FAA could have intervened but didn't, I think, makes for a good narrative. I don't think it stands up all that well to scrutiny. I think the Max case is sort of fascinating, simply because what I think the Max case really exemplifies more than anything is Boeing's management losing sight of its own incentives. There's lots been written about Boeing's management culture and it becoming a sort of culture of kind of bean counters and people trying to maximize profits, rather than being a kind of engineering culture that really quite understood the implications of the kinds of choices that they were making. But I mean, I agree completely, I think, for the most part.
John, in the aircraft case, what did you make of the role of pilots? Because it seems to me that I think it was pilot organization that introduced the no fault reporting, or at least argued for it. That when there were air misses and so on, that the reporting mechanism is through was originated through the pilots, not through the airframers or the operators. And so I do think that they have a kind of professional role there, and so that's rather distinctive. The other thing I would say is, of course, the thing about airframes is that only a tiny number are manufactured every year. I mean, even if you look at the 737-300 or the variants from 300 to 500, the max number that were produced in a year was just over 200. Yeah, which is absolutely minute by comparison with a car. And actually, the producing avionic components is kind of done on a shoestring, because actually the return on it is quite small. You know, if you think about how many copies you have, yeah, then actually you have to push all the development costs into a relatively small number of copies in terms of the core systems of these aircraft. So actually, it's a very, very different situation from a car, where you can afford maybe to do a lot of design work, but then you're talking about a couple of cents making a difference between whether somebody gets the contract or not. So it's really very different.
Yeah, no, I could talk about this all afternoon, so you're gonna have to sort of mute me if I go on too much. But yeah, I think comparing jetliners with cars is a difficult sort of comparison. The levels of reliability you require of these two systems is radically different by orders of magnitude, I think. In terms of, if you think about the complexity of the system and so on, right? I think that jetliners are better compared to something like reactors that require sort of equivalent sort of levels of reliability. I would say argue sort of equivalently complex systems. They're both sort of need to actively work in order to stay safe. And I think they make for a decent comparison. And then compared with reactors, we build tons of jetliners, right? We build, we fly tens of thousands of them every day, and there's what, 400 reactors involved. And then,
well, there are tens of thousands of flights. There aren't that many copies of the actual aircraft. But anyway,
I mean, every flight you have to have an aircraft, right? So I mean, there are tens of thousands in operation. Well, I guess you could have multiple flights in a day, but
yep.
The I can't remember what I was going to say. And I think again, this is something that I need a lot more time to sort of justify, but I think a really interesting sort of facet of civil aviation is just how similar airframes are to each other, right? So it's one thing to say that we've only built a few copies of this one, the 737-200 or something. But when you look at the degree and depth of design commonality and then this kind of shared airframe paradigm across all sort of manufacturers, I think has contributed a lot to the fact that the reliability of jetliners, that we've been iteratively sort of honing this one kind of common paradigm that we vary, we stretch a bit, and then for the max we move the engines, and often some of these variations turn out to be very important, but they are still sort of variations on a sort of very common theme, right? We haven't changed the belt buckles of airplanes for 60 years. That's half the history of powered flight, right?
Mm-hmm.
I think that's important to. So I would argue that we actually fly quite a lot. I mean, certainly nowhere near as many as cars, right? But which again, I think we have to understand the incentive structures around car manufacturers in relation to how many cars there are on the road, right? If they build something that's imperfect, that's going to become evident very quickly, right? And they're not going to be able to get away with it, right? You could build a reactor that was 100th as reliable as it's supposed to be, right? 2 orders of magnitude, and it's still, you wouldn't expect it to melt down for decades, right?
Well, at least in UK, then. I mean, you probably know much more about this than me. Then there are claim limits on what you can claim for any one safety element within a reactor. I think it's 1 failure in 10 to the 4 is the max you can claim. And what that does is it pushes their structure into kind of defense in depth. Yeah. Whereas with an airliner, then a FADEC failure. Yeah. I mean, I think Lucas Aerospace put a small hole in their FADECs at one point, and during a thunderstorm, 4 engineer craft had all of them go out simultaneously. Yeah, which is kind of unusual, but I mean it's a common mode failure, and of course these things are susceptible to that kind of thing. So I think that the structure of the regulation in comparing nuclear to avionics is very different, actually. That there are quite a large number of single points of failure in aircraft. Maybe.
Sorry.
Anyway, sorry.
No, I would argue that both systems do try in justifying the reliabilities that they claim. They lean both of them lean very heavily on sort of defense in depth or systems engineering, right? So this is, you have multiple engines on an airplane just in case one goes out. You have redundant everything, load path in the airframe structure, avionics. The airplanes are designed to be, as far as possible, redundant in every dimension, and just as and of course, as you point out, putting these things together, it requires a bit of theory, right? You have to have a sort of mental model of how everything relates, but it's exactly the same with nuclear plants, right? The Fukushima's defense in depth, they put lots of, had multiple generators, but it put them all underground, which created a sort of common mode failure when it was flooded, right? So there was a sort of theory about how these things could fail, right? And I would argue that it's very, very similar with jetliners, and then the sort of
high reliability engineers in the room. So we maybe divert from this really important point. Pete, you raised a question which I'd like you to pose again and put and more and maybe generalize about this issue. Pete, welcome, by the way.
Hello. Hi everyone. I guess it's a question that we have uncovered, identified so far in the project so far. But I think it taps into how we do assume that self-driving cars are progressing quite well. But I think one of the things about this matter of evolving functionality, which is quite interesting, is that there is still a significant amount of control over the rollouts of the software updates over the year. And yeah, I mean, that was my point really. But is there a specific question, Robin, that you wanted to ask or something? Or
well, you made a point about it being more difficult to roll out a general over-the-air update to all self-driving cars.
Yeah.
That made me think about the question about how liability and control, it links into the point that Stuart made about configurability.
Yeah.
And what happens where the configurability of devices and the use of devices is controlled by both the manufacturer and the deployer, and what does that do then to our model of regulation?
Yeah.
I thought you were making a point about that, so that it struck me that was very pertinent to these questions.
Yeah, no, it is about that really, and I think that's something that it's just evolving, and we don't know ourselves, and I think we need to start thinking about I think Stuart was tapping into this kind of localization. He made a point about, my Tesla is going to be different to your Tesla. So, for example, a small city, small town, village Tesla is going to be different in terms of functionality, to the way it operates in a big city, urban environment, and there'll be more accidents. It'll be learning differently. And you can't just, from a kind of an operational point of view, you can't just roll out like it's done with our Windows or Mac operating systems. You can't just roll out a blanket patch over the air to all devices, right? What's happening now, because each Tesla will be learning differently and experiencing different interactions with its environment, with different kind of edge cases and things like that. Each one will be developing its own unique data set, which will be feeding back to Tesla HQ. So it just opens up the question of each Tesla is different. So how do you manage the operation and the safety? How do you roll out a patch? So it just raises a notion. Does that mean you need to kind of roll out an over-the-air update in terms of safety, map updates, the way it operates? You have to almost basically send out an update that's specific to each car as well. And also, Stuart raised a really important thing, and I completely haven't considered this, but the drivers have their own freedom, choices to configure. They have a degree of freedom in configuring their cars to an extent, and how much of that is actually factored into the Tesla HQ in terms of these over-the-air software updates as well. So it's just asking questions, and we're trying to feel our way through the literature at the moment. And just Stuart, yeah, he's just raised some two really important points in my opinion.
Use my position in chair because that's touched on. We were looking at SAP and enterprise system software, its performance, which often it fails in companies, and actually just deciphering whose responsibility that is would take an infinity of time.
Oh yeah.
But SAP has a kind of a simple razor for finding it out, and they say, well, run your standard software, run the vanilla software on your site. And if the failure is happening there, then that's our problem. And if the failure isn't happening, that's your problem. So it's worked out a routine. It's technically unsupportable, legally nonsense, but actually provides a kind of pragmatic solution to the otherwise irresolvable problem about what had actually caused this error to emerge. And it seems to me that those kinds of routines will be an essential feature of the world of, I can't remember what you said, John. It was kind of, the practical doing of the governance of AI. We will have to have those practical routines for actually doing that. Look, we've come to an end. Some people have said goodbye. Are there other people who want to ask questions, or should we wind up the formal session now? Maybe we could have an informal chat for whoever hangs on. I think I should. It is an opportunity to say thank you, John. That was very interesting. I have to say there was also one comment that was so high up in the chat you may not have seen it. Enormous synergies of interest between what our TAS node is doing and what you're talking about. I think there's and I would say the kind of issues that you're raising are fiercely in line with the kind of issues that we're interested in exploring further. So we're glad to see you, and we hope this is a discussion that we can continue. Stuart has reminded us of the correct way to applaud with our happy electronic hand. Those look almost like